Hello everyone. Welcome to another episode of Deep Dive Knowledge. Hello. I read the summary of your report on large language model, LLM-based autonomous agents, and I'm really interested in learning more. Could you please explain to me what exactly is a large language model and how it is used in the construction of autonomous agents?
Certainly. A large language model, LLM, refers to a powerful artificial intelligence model that is trained on vast amounts of text data, typically from the internet. It is designed to understand and generate human-like language. LLMs have been successful in achieving human-level intelligence by leveraging comprehensive training datasets and a large number of model parameters. Now, let's talk about how LLMs are used in the construction of autonomous agents. In the field of autonomous agents, researchers have recognized the potential of LLMs as central controllers for these agents. The key idea is to equip LLMs with human-like capabilities such as memory and planning, enabling them to behave like humans and make decisions in various tasks effectively. To achieve this, researchers have developed different models that incorporate LLMs as the core component. These models aim to enhance the decision-making capabilities of autonomous agents by leveraging the knowledge and language understanding capabilities of LLMs by using LLMs. Autonomous agents can learn from vast amounts of text data and make more informed and human-like decisions. The integration of LLMs into autonomous agents allows them to understand and generate natural language, enabling them to interact with humans more effectively. This opens up possibilities for applications such as virtual assistants, chatbots, and language-based decision-making systems. In summary, LLMs are powerful language models trained on large amounts of text data. When used in the construction of autonomous agents, LLMs enhance the decision-making capabilities of these agents by providing them with human-like language understanding and generation abilities.
Thank you for the explanation. It's fascinating how LLMs can be integrated into autonomous agents to enhance their decision-making capabilities. In your report, you mentioned a unified framework for the architecture design of LLM-based autonomous agents. Could you please elaborate on this framework and how it contributes to the development of these agents?
Certainly. In our report, we propose a unified framework for the architecture design of LLM-based autonomous agents. This framework is a comprehensive and systematic synthesis of existing research in the field. The architecture of an autonomous agent plays a crucial role in leveraging the capabilities of LLMs and enabling the agent to perform various tasks effectively. The unified framework we propose aims to provide a structured and organized approach to designing the agent architecture. The framework consists of several key components. Firstly, it includes modules for preprocessing and feature extraction, which are responsible for preparing the input data and extracting relevant features that the LLM can work with. This step ensures that the agent receives the appropriate information to make informed decisions. Next, the framework incorporates a module for decision-making, which utilizes the power of LLMs to process and analyze the input data and generate appropriate responses or actions. This module is designed to take advantage of the natural language understanding and generation capabilities of LLMs. Additionally, the framework includes a memory module, which allows the agent to store and retrieve information as needed. This memory component is essential for maintaining context and knowledge over time, enabling the agent to make informed decisions based on past experiences. Moreover, the unified framework emphasizes the importance of continuous learning and adaptation. It incorporates a module for model updating, which enables the agent to learn from new data and improve its performance over time. This aspect is crucial for autonomous agents to keep up with evolving environments and tasks. By providing this unified framework, our report contributes to the development of LLM-based autonomous agents in several ways. Firstly, it provides a comprehensive overview of the different components and their roles in the agent architecture. This understanding allows researchers and developers to design and implement more efficient and effective autonomous agents. Secondly, the framework serves as a guide for researchers and developers, enabling them to compare and evaluate different approaches in the field. It helps in identifying the strengths and weaknesses of existing methods and facilitates the development of novel techniques and improvements. Overall, the unified framework for architecture design of LLM-based autonomous agents presented in our report offers a structured and comprehensive approach to building these agents. It provides a foundation for further research and development in the field, ultimately leading to more advanced and capable autonomous agents.
Thank you for the detailed explanation of the unified framework. It's clear that the framework provides a structured approach to designing the architecture of LLM-based autonomous agents. In your report, you also mentioned the diverse applications of these agents in social science, natural science, and engineering. Could you give me some examples of how LLM-based autonomous agents are being used in these fields?
Certainly. In the field of social science, LLM-based autonomous agents have found applications in areas such as political science, economy, and social simulation. For example, in political science and economy, LLM-based agents have been used in studies like Out of One and Horton to analyze and model complex social phenomena. In social simulation, LLM-based agents have been employed in projects like simulacra and generative agents to simulate and study various social interactions and behaviors. These simulations can help researchers gain insights into societal dynamics and make predictions about social phenomena. Moving on to natural science, LLM-based autonomous agents have been utilized in areas such as experimental assistance and science education. For instance, in the field of experimental assistance, agents like ChemCrow and Boyko et al. Have been developed to assist scientists in conducting experiments and managing data. In science education, LLM-based agents like NLSOM and CodeHelp have been employed to provide educational support and assistance to learners. These agents can help students with tasks such as generating explanations, providing examples, and answering questions related to scientific concepts. Lastly, in the field of engineering, LLM-based autonomous agents have been used in areas like civil engineering and computer science, software engineering. For example, in civil engineering, the IGLU system has been developed as an autonomous agent to assist with tasks related to civil engineering projects. In computer science and software engineering, agents like MetaGPT and ChatDev have been utilized to aid developers in various tasks such as code generation, bug detection, and software documentation. These are just a few examples of how LLM-based autonomous agents are being utilized in social science, natural science, and engineering. The applications are diverse and range from research support to education and practical assistance in various domains.
Thank you for providing those examples. It's impressive to see the wide range of applications for LLM-based autonomous agents in fields like social science, natural science, and engineering. In your report, you mentioned the evaluation strategies commonly used for these agents. Could you please explain what these evaluation strategies entail and how they are used to assess the performance of LLM-based autonomous agents?
There are two commonly used evaluation strategies for LLM-based autonomous agents: subjective evaluation and objective evaluation. Subjective evaluation measures the capabilities of the agent based on human judgments. It is suitable for scenarios where there are no evaluation datasets or when it is difficult to create such datasets. In subjective evaluation, humans evaluate the performance of the agent and provide their judgments. This evaluation strategy is important because LLM-based agents are usually designed to serve humans, and human judgments reflect the criteria that are important to us. However, subjective evaluation also has some challenges, such as high costs, inefficiency, and population bias. To address these challenges, researchers have explored using LLMs as proxies to conduct subjective evaluation. For example, in the ChemCrow project, researchers assess the experimental results using GPT, a type of LLM. They consider both the completion of tasks and the accuracy of the underlying processes. Another example is ChatEval, where multiple agents are used to assess the outcomes produced by candidate models in a debating manner. With the progress of LLMs, using LLMs for subjective evaluation can become more credible and applicable in a wider range of applications. Objective evaluation, on the other hand, refers to assessing the capabilities of LLM-based autonomous agents using quantitative metrics that can be computed, compared, and tracked over time. This evaluation strategy focuses on measurable aspects of the agent's performance. Objective evaluation allows for a more systematic and quantitative assessment of the agent's performance, making it easier to compare different agents and track their progress over time. Examples of quantitative metrics used in objective evaluation include environment simulation, social evaluation, multitask evaluation, and software testing. In summary, subjective evaluation relies on human judgments to assess the performance of LLM-based autonomous agents, while objective evaluation uses quantitative metrics to measure and compare the capabilities of these agents. Both evaluation strategies are important for understanding and improving the performance of LLM-based agents.
Thank you for elaborating on the evaluation strategies used for LLM-based autonomous agents. It's interesting to see how subjective evaluation, with the use of human judgments, and objective evaluation, with quantitative metrics, provide different perspectives for assessing the performance of these agents. In your report, you also mentioned challenges and future directions in the field. Could you please highlight some of the key challenges and potential future directions that you identified?
In our report, we have identified several key challenges and potential future directions in the field of LLM-based autonomous agents. These challenges and directions were derived from previous studies and discussions in the field. One of the key challenges is the design of the agent architecture to better leverage LLMs. LLMs have shown great potential in improving the performance of autonomous agents, but there is still a need to explore and develop effective architectures that can fully leverage the capabilities of LLMs. This involves designing architectures that can integrate and manage large-scale language models, as well as optimizing the interaction between the agent and the language model. Another challenge is enhancing the agent's capability to complete different tasks. While LLMs have demonstrated impressive language understanding and generation abilities, there is still a need to develop techniques to effectively incorporate task-specific knowledge and reasoning into the agents. This includes exploring methods for transfer learning, domain adaptation, and reinforcement learning to enable the agents to generalize and adapt to different tasks and environments. Furthermore, the evaluation of LLM-based autonomous agents poses a challenge. Traditional evaluation metrics may not be sufficient to assess the performance of agents that heavily rely on LLMs. New evaluation strategies need to be developed to measure the agent's language understanding, generation, and decision-making abilities accurately. This includes exploring techniques for benchmarking, simulation-based evaluation, and human evaluation to provide comprehensive assessments of agent performance. In terms of future directions, one potential direction is the development of more efficient and scalable architectures for LLM-based autonomous agents. As language models continue to grow in size and complexity, there is a need to explore techniques for efficient deployment and execution of these models on different studies, including edge devices and distributed systems. This will enable the deployment of LLM-based agents in real-world scenarios with limited computational resources. Another future direction is the integration of multimodal capabilities into LLM-based agents. While LLMs excel in language understanding and generation, the ability to perceive and understand visual and auditory inputs is crucial for many real-world applications. Exploring methods for incorporating multimodal information, such as images, videos, and speech, into LLM-based agents will enable them to interact and understand the world in a more comprehensive manner. Lastly, there is a need for further research on the ethical and societal implications of LLM-based autonomous agents. As these agents become more advanced and autonomous, it is essential to address issues such as privacy, fairness, and accountability. Developing guidelines and frameworks for responsible development and deployment of LLM-based agents will ensure that they are used ethically and for the benefit of society. Overall, the field of LLM-based autonomous agents is still in its early stages, and there are numerous challenges and exciting future directions to explore. By addressing these challenges and pursuing these directions, we can further advance the capabilities and applications of LLM-based autonomous agents.
Thank you for outlining the key challenges and potential future directions in the field of LLM-based autonomous agents. It's clear that there are still many areas to explore and improve upon, including agent architecture design, task-specific knowledge incorporation, evaluation strategies, efficiency and scalability, multimodal integration, and ethical considerations. By addressing these challenges and pursuing these future directions, the field can continue to advance and enhance the capabilities of LLM-based autonomous agents.
Certainly, in the field of LLM-based autonomous agents, there are several key challenges and potential future directions that researchers are actively exploring. These challenges and directions shape the future development and advancement of LLM-based autonomous agents. Let's discuss some of them. 1. Model performance and scalability. One of the key challenges is improving the performance and scalability of LLM-based models. While LLMs have shown impressive capabilities, they are computationally expensive and require significant computational resources. Future research aims to optimize these models to improve their efficiency and scalability, allowing them to handle larger and more complex tasks. 2. Interpretability and explainability. LLM-based autonomous agents often suffer from a lack of interpretability and explainability. These models are highly complex and their decision-making processes can be difficult to understand. To address this challenge, researchers are exploring methods to make LLM-based agents more interpretable and provide explanations for their actions, enabling users to trust and understand their behavior. 3. Ethics and bias. LLM-based agents can inadvertently inherit biases present in the data they are trained on. This raises concerns about fairness, accountability, and the potential for biased decision-making. Future directions include developing methods to detect and mitigate bias in LLM-based models, as well as ensuring ethical considerations are integrated into the design and deployment of these agents. 4. Generalization and transfer learning. LLM-based agents often struggle with generalizing their knowledge to new tasks or domains. They typically require large amounts of task-specific training data. Future research focuses on improving the generalization capabilities of LLM-based agents, enabling them to transfer knowledge across different tasks and adapt to new environments more effectively. 5. Interaction and collaboration. LLM-based autonomous agents are often designed to interact and collaborate with humans and other agents. However, effective interaction and collaboration are still challenging. Future directions include developing more natural and seamless communication interfaces, as well as studying the dynamics of multi-agent systems to enhance collaboration and coordination. 6. Robustness and safety. LLM-based agents can be vulnerable to adversarial attacks and may exhibit unsafe behaviors in certain situations. Robustness and safety are critical considerations in the development of LLM-based agents. Future research aims to improve the robustness of these agents against attacks and ensure their safe and reliable operation in real-world scenarios. These challenges and potential future directions highlight the ongoing efforts to advance the field of LLM-based autonomous agents. By addressing these challenges and exploring these directions, researchers aim to unlock the full potential of LLM-based agents and pave the way for their widespread adoption in various domains and applications.
Thank you for elaborating on the challenges and potential future directions in the field of LLM-based autonomous agents. It's evident that researchers are actively working to improve the performance, interpretability, ethics, generalization, interaction, and safety aspects of these agents. By addressing these challenges and pursuing these future directions, the field can continue to evolve and enable the development of more advanced and reliable LLM-based autonomous agents.